All right. So any questions? No. All right. So our goal today is to basically solve more or less the differential equation we wrote down last time. And so we're seeing, we want to see structure formation. Okay. So we're going to push this linear differential equation more or less as far as we can. And then we want to make some comments as to what happens at the nonlinear level. The nonlinear level would be relating to ultimately forming structures like galaxies, galaxy clusters, and so on. Okay, and we're going to do this in two parts. We're mainly going to imagine a hypothetical situation where all the matter in the universe is dark matter. Now, after all, it's about 85% dark matter and 15% baryons. So this is a pretty good first start. And then either, hopefully there'll be time by the end of today, or if not next time, we'll then wonder what happens when we include the baryons. Okay. Okay, so let's look from, recall from last time. Got this nice second order differential equation. Right? Or in K-space, we can just write this thing, but maybe hats occasionally if I'm in K-space. All right. So these are the equations, well, either equation we can try to solve. And what we should really be thinking about, if we were to do the full analysis, would actually not just to write down this equation, but to write down a sequence of equations, considering the fact that there are multiple species, right? So we could write down something like this for the dark matter, something like this for the baryons, and so on, right? But as I said, as a first pass, so this is it turns out to be a very important starting point. We'll just focus on dark matter. Okay, so dark matter only. But by that I mean, to be clear, I just mean no baryons. So by this I mean that the backgrounds, although we may not have phrased it like this, we can pretty much get away with these kinds of equations even if the background is not matter. Right? We might be in the first 47,000 years of the universe where we had radiation domination. We can imagine that's what's controlling Hubble and so on. But the perturbation in the matter is just dark matter. It's all dark matter, right? So we're just deleting the 15% baryons to organize our thinking. And we could even use this in the late universe where we're dark energy dominated, right? So the background is dark energy, but the stuff we're interested in is matter, namely the dark matter. Is that all right? Okay, and the simplification that comes from dark matter is that dark matter has negligible pressure. And associated negligible sound speed. So the CS is much, much, much less than the speed of light. We can more or less just set it to 0. Okay, that won't be true for the baryons, which are talking to the photons in the early universe. Okay, for the first 380,000 years, there's this coupling between the baryons and the photons. And the baryons sort of participate in this fluid with the photons and have a significant sound speed. And we'll either talk about the end of today or next time what the value of that sound speed is. But for the dark matter, they don't talk to the photons, so there's nothing to provide significant pressure for them. Okay. You could say that they're particles and they have motion, just like the air in this room. There's some pressure, there's some sound speed, but that sound speed is orders of magnitude less than the speed of light. And when you're in that situation, it will not have much of a bearing on these equations. Yeah. Potentially it could, but okay, maybe I should even give this a name. Some people call this cold dark matter. Okay. Cold dark matter. CDM. And so the most, let's say, vanilla model for dark matter that more or less fits the data at the moment is one that has negligible self-interactions. That's a very interesting question, whether there is some. But for large-scale structure, we have yet to detect significant self-interactions. So this is more or less compatible with the data. All right, now if we set the CS term to 0, you can see, by the way, whether or not you choose to study things in position space, right? So a reminder here is delta as a function of x and t. If you go to momentum space or k space, it's a function of k and t. We often write delta sub k of t. And in position space, a reminder that we're writing rho as the background value, which is a function only of time. 1 plus delta is the perturbation, the fractional change from homogeneity, the density contrast. But if you ignore the sound speed, the structure of these two terms, you can see these two equations will look identical if you delete the CS. Okay, so ignoring CS, I can just write the same equation. Okay, and you're allowed to picture that delta as a delta of x or a delta of k because it has the identical same equation. Is that clear? That's up to you whether you want to put a hat on that delta or not. Yeah, and maybe I'll just write maybe a little d here to remind us that this is an equation for the dark matter. Cold dark matter, if you like. Doesn't matter. And we're going to have to deal, so, okay, you have a differential equation, which is not too bad. One needs to know initial conditions to solve this thing. And we'll talk about the initial conditions in some detail, probably next time. And there, it will turn out, for reasons we can discuss, that it will be a little easier to talk about initial conditions in K space rather than position space. But for now, we don't need to worry about that. We just have this equation in either space. All right. Now, this prefactor here, we can write that in a slightly more useful way. So first of all, I can write rho bar. We can write this as rho bar of the dark matter times omega of dark. No, I'm writing that. Wait a minute, that's not how I want to write this thing. Let me go the other way. Sorry, the problem is the dark matter is feeling a gravitational interaction from other pieces of dark matter, right? So this rho here has to be the rho of the dark matter itself. Does that make sense? Okay, so this is, let's put an M there for matter or dark matter, because I'm assuming all the matter is dark matter. Are we okay with that? Yeah. This is the term that comes from the Poisson equation. The Laplacian of phi Newton is sourced by the density perturbation. And so it's the dark matter that fills the universe that provides this. And for example, the background dark energy and so on is irrelevant to the perturbations. Okay, so that's what I want to do here. So, okay, so try again. So rho bar for the matter is the contribution to the universe from that. We define this always as omega matter times the total. Right? That's just been the definition of omega. It's just the fractional contribution of that component. I just use that because it's a little convenient. And so now, let's go a little further. I put in a 4 pi g. All right, and now I'm going to write this as I pull out the omega matter. I'm going to write this as 8 pi g over 3 rho bar times 3 halves. Okay, all I did was multiply and divide by 3 halves. Okay? And so what is this thing? I did that for some reason. That's h, or h squared. Right? By the Friedmann equation, this is Hubble squared. We can put that in here. This is 3 halves omega matter Hubble squared. Okay, so now that gives us a better idea as to the structure of this equation. So the perturbations in the dark matter looks like this, minus 3/2. Okay. So remember, this is the term coming from somehow the local gravity between inhomogeneities in the dark matter. They're attracting one another, trying to give rise to a gravitational instability. And it depends on the fraction of dark matter that fills the universe, the background value, Hubble squared. And then there's another kind of Hubble friction term, if you like, which is also set by H. Okay? The H is controlling two things at once. All right. So questions about this equation? All right, so we're going to solve this. I mean, this is the kind of equation you could easily put this on a computer and solve that thing. From the early universe that's radiation dominated to matter to dark energy, right? Because we can more or less have a plot of H versus T, just solving the Friedmann equation. So you plug that in. And then correspondingly, there's the percentage of the background matter in the universe. So omega matter versus T. So you could feed in those two functions and then solve this equation numerically. All right, but on the board, what we're going to do is solve it analytically in three important cases. Deep in the radiation era, deep in the matter era, deep in the dark energy era. And we can kind of hook these onto one another. Okay, so step one is radiation era. So that's T much less than 47, well, T equality, which is 47,000 years. Let's solve this equation in that era. So you're radiation dominated. So this means that omega matter is negligible. The scale factor is proportional to T to what? How does the scale factor depend on time in the radiation era? T to some power. Can you speak up? Sorry. 1/2, that's right. Yep, A is T to the 1/2. Okay, and then Hubble is A dot over A is 1 over 2T. All right. So I put that in here. We just have delta double dot. And then there's a 1 over 2T, and then there's a 2. So the 2's go away. And the last term is negligible in that era. So this is our equation. Not bad. Right, so can anyone tell me some solutions of this differential equation? Think of at least one solution. Yeah. No. Okay, that one's too simple. I'm not going to accept 0. We have to do a little more than that. There's one solution to this that's really, really, really simple. It's almost the 0 of this equation. There's a really boring solution. So notice that we've turned off this term, which had no derivatives. So every term here has derivatives. So if every term in your differential equation has a derivative, what's at least one boring solution? Say again? A line, so a constant. Do you mean line as in flat line or a constant? Right. So one solution is delta D equals to a constant. No, I'm going to call that A for some reason. Right, because then both terms just differentiate to 0. But then there's another solution which depends on time. And this is one that, well, I don't know if anyone can guess another solution. Maybe not so obvious. But well, let me just state that unless All right, another solution of this, I mean, we could get it because we could define a variable called delta dot and then use separation of variables and derive it directly. But another solution is a log. Okay. So let me just state that the general solution I'm going to write as this constant, and then I'm going to add log t. Okay. And a and b are just arbitrary numbers. It's a second order differential equation, so it should have two parameters to specify all solutions. And we can just check that this is correct. So with my solution here, we get b over t. And then the second derivative of that thing is minus b over t squared. Okay, so you see if you, divide this first term by t, you get t squared, and then they cancel. Now, often we'll want to, we can express things as a function of time. That's perfectly fine. Or we might often express things in terms of the scale factor. Okay, and here, remember, the scale factor is proportional to t to the half. So an equivalent way of writing this thing is we could just write delta d in terms of the scale factor is, well, you could you could do a substitution and say that t is like a squared. I could write log of a squared, right? Well, log of a squared is 2 log a, and I can absorb the 2 into the b and just give it a new name, b twiddle or something. Okay, so this is just as good a way of writing it, right? Log a, maybe a twiddle, doesn't matter. Okay. All right, so the punchline then is that if we let this system go, this little overdensity delta is going to grow in time, but only very, very slowly, just as a very slow logarithm. Okay, it's not in this limit, the local density contrast, the local gravitational pull between the dark matter is a very small correction to this equation because we're radiation dominated. So we're just studying this reduced equation. Okay, and then it's a bit, I don't know if I have great intuition as to why there's any growth in this thing, but it's somehow that there's this background radiation and there are these dark matter perturbations on top of that. All right, and they're just coupled to the background ultimately through gravity. So implicitly, that's what this term represents. And I guess there's some, if you evolve that system, I guess there's some slippage, if you like, between the behavior of one and the other. I don't know if I have great intuition for it. But it's this very mild growth, okay? And since the local dark matter inhomogeneities are not playing a role because that term wasn't there, we should expect it to not grow very much. It will grow a lot faster in the matter era that we're coming to in 1 minute. Okay, so let's just summarize. Here we have very slow log growth. Okay, but it's not nothing. Okay, so if we imagine an inhomogeneity laid down, let's say when the universe is, I don't know, a second old, and you evolve that for the first 47,000 years, well, you're going to pick up some log enhancement where you think about the ratio of 47,000 to a second. So something like that kind of enhancement. All right. So is everyone cool with that? Okay, so the next thing we want to think about is in the matter era. So this is 47,000 years, let's say, is much less than the time of interest, much less than about 10 gigayears, which is roughly when dark energy takes over. Yeah. Well, okay, you can write it like that if you want. In terms of scale factor, we don't need to remember that. But in this case here, yeah, I could write t over some representative time. That's true. But the way I've written it is not, I mean, that's probably a more useful way of expressing it is what you're saying. What I've written here is not wrong, because if I write log of t over t naught, where t naught is some reference time, I can then use the fact that that equals log t minus log t naught and absorb the log t naught in what I called a. So this is okay. But I agree that that ultimately what you're saying is probably a more useful way of presenting it. To lay down this log at lay down the t or the a with respect to a reference scale factor or reference time. Okay. But you agree that that's okay as written. Formally, it's okay. All right. So in the matter era, right, what do I want to write now for omega m? What's omega m in the matter era? Omega, not the scale factor, but this capital omega. The initial, it doesn't necessarily, it could grow, but I claim it's even simpler than that. Deep in the matter era. That's the scale factor. So let's put that there. What you say is correct for the scale factor. A is proportional to t to the 2/3, which by the way means Hubble is 2 over 3t. But omega matter is something else. It's just one, yeah. Omega matter is just, by definition, right? It's just a fraction of the universe. Let's write it here. Omega matter means rho bar matter over rho bar. Just a fraction. So we're in the era where we're matter dominated, so this is basically one. Okay, in this time interval. Okay, so now our differential equation, we've got to plug in that Hubble 2 over 3t and omega m of 1. So maybe we'll put it up on this other board. Now we have a slightly more interesting differential equation. Okay. So this is our equation in the matter era for a little density perturbation. So this equation, actually, as was this equation, I mentioned to you last time at the end that we worked hard to get this factor of 2. So these factors here matter, right? The fact that that's 1 over t is essential that this is a log, right? And the fact that these have a 4 here and a 3 and all this stuff will be incredibly important to the actual solution. These are not just some random numbers that you can change by a factor of 2 and expect things to be the same. Prefactors in a differential equation like this matter a lot. Okay, so this is a differential equation that has a nice structure to it, however. Okay, somehow you see that every time you lose a derivative, you get a 1 over t that has a progression. And we go down by t, then we go down by t squared. Okay, so that means that this equation is actually not so bad. There is a way of solving this thing. Does anyone know a strategy for solving these kinds of equations? Like what? Yeah.
My first instinct is to try to come up with some power law like t to the n over it. It looks like you'll get the right tendency.
Right.
The right n.
Okay, yeah. So we'll call it, okay, I'll use your language t to the n. So we'll try, doesn't matter, we'll call, I don't know, prefactor doesn't matter, a t to the n as you call it. Okay, so we're just going to try this. And then our goal is going to be to solve for n. Okay, so we plug this in, so delta d dot a n t to the n minus 1 second derivative. All right, so we plug it in. Like this. Okay, it's a linear differential equation, so this A doesn't matter. And indeed, the T's are going to balance. That's the beauty of that structure. So everything is proportional to T to the N minus 2. Let's just stare at this thing for 1 second. N minus 1. Minus 2/3. Okay, so it's just a quadratic equation for N. There it is. And let's just write down the solutions. The solutions of this quadratic, 2/3 or minus 1. That look right? So let's say 2/3 or minus 1. Yeah, so we have these two solutions, and you see there's a positive power and a negative power. Okay, that means we have a growing mode and a decaying mode. Right? Last week, when we just imagined we were expanding around a static background, right? We got in the limit where K was less than K genes, right? We got a growing mode and a decaying mode there. What do we remember? What was the structure of our growing and decaying modes from last week when we expanded around a static background? What kind of growth was it? It was exponential, right? Yeah, last time we got exponential growth or exponential decay. The sum of the two, the growth wins, of course, at late times. But now we have power law growth and power law decay. So this system now is in this expanding background. You can think of this as a kind of Hubble friction term. And the background's preventing this thing from having this exponential explosion in growth. But power law is pretty good. It's certainly a lot better than log growth. But this is still significant. But it's not exponential. Okay, so our solution, I can write delta D, general solution. Using the A and B notation, we write A, A over T, let's say, plus B T to the 2/3. Or, as we'll often do, we'll write it in terms of scale factor. And we just remember that A is proportional to T to the 2/3. So this becomes I don't know, twiddle, if you do a rescaling. Okay, so the growing mode here is actually proportional directly to the scale factor itself. T to the 2/3 is in fact A. Okay, this is a somewhat, I don't know, famous result that in the matter era, perturbations just grow linearly with the scale factor itself. Right? Scale factor grows by 1,000, your perturbation grows by a factor of 1,000. Right? In these equations, you almost always just want to focus your attention on the growing piece. Well, with the log, there's a little subtlety because of the constant, but anyway, the growing piece completely dominates at late times. Okay. Yeah, so power law growth. Okay, and then finally we can do the dark energy era. So this is times much bigger than 10 gigayears. In a way, we haven't really experienced that much yet. I mean, we're only up to 70% dark energy, but we can understand the asymptotics as to where things are going to match all these, link all these behaviors onto one another. Is that okay? So if you imagine going to the far future, omega matter then again is negligible. You're dominated by dark energy. And if this is indeed vacuum energy, then A is proportional. In this case, what? What has a scale factor go in this era? We could just have a cosmology or constant, as it's called. Just T? No, it's a bit more exciting than just T. Sorry. We sometimes call this de Sitter space. It's exponential, yeah. The A is e to the constant Hubble, which we sometimes call HVT. Yeah, and all I'm writing for H is that it's a constant. Okay, so then our differential equation, well, I can just write it, is delta D double dot plus 2H, and I'll just put a V subscript to remind us it's a constant, delta D. And then the other term is negligible in this era. We can write down the general solution of this thing. So again, can anyone tell me one solution, first of all, of this equation? A constant. Constant does the trick. I can write A. And then there's another interesting solution. What's another solution of this thing? Yeah. Exponential. And is it a growing or decaying exponential? Decaying, yeah. So we got to cancel this term. So I can write, let's say, B e to the minus 2 HVT. Right? Take that derivative. You'll pull down a minus 2 HV. That will cancel this. Is that clear? It's not clear, you should double check. Okay, so that's the solution. If our universe is indeed entering a phase of vacuum energy domination, there is no growing mode at all. Okay, so maybe actually if some sense, let me flip my notation slightly in a way. I could call that B and A, where the B is the one, the prefactor of the term that dominates at late time. It would be the consistent notation. And in terms of scale factor, we can also write this as B plus A over scale factor squared. Okay, so when you have this dark energy, it really doesn't like perturbations to grow. Okay, some part of the perturbations will just decay away and the other bit will stay frozen. Okay, so dark energy is a kind of an enemy to growth. Okay, the universe is, well, if you like, it's because the universe is growing so much, the background is growing so much, that the little dark matter inhomogeneities are just spread out too much in a way, that they struggle to grow in their density contrast. But they don't disappear, they can maintain a density contrast. It doesn't disappear. So that's something. Right? You could imagine super exponential growth in the background. If it was even faster than this, then you can get solutions where both of them are decaying. So it's not quite as bad as that. But anyway, this is what it looks like. All right, so let's try to put these things together. Any questions about all this? Yeah. Yeah. Right. Yeah, good. So maybe we should draw some pictures about that. Okay, so let's say we look at, I can either plot delta for you, which we've been drawing, right? If I plot delta, it has a mean of 0 by definition. But we can also remember that, let's see, so let's write rho. Remember, is rho bar 1 plus delta, the density contrast. Or maybe we can divide both sides by rho bar and have a look at this, 1 plus delta. Okay, so delta 0 is just the mean, it's just boring. So let's say we plot that function. The density over the mean density of the universe. Okay, so here's 1. This is position x at some moment in time. Okay, so I have to give you an initial delta. These equations are not going to predict the initial value. Those are initial conditions that we either just measure, or better yet, we may have a theory for the initial conditions. Okay, we'll talk about that in the coming lectures. But in any case, for now, let's just say that there's an initial delta, which maybe it looks like this. I don't know, some wiggles here and long wiggles there. It can be a messy initial state. So let's say that this comes from delta at some t, I don't know, time t1 or t initial. Maybe I'll call it initial. Now, what we found is if we just, let's say, focus on the growing modes here, that they just scale in some function of time. Like this one is the most interesting here. Okay, so you give me some initial value, then it just grows like t to the 2/3. So if I draw that, it means delta just somehow increases, t to the 2/3 in the matter era. Let's summarize how people write this actually. So if you focus on growing mode, in any of these eras, I could write delta, let's say of t, is some prefactor that I was calling b times some f of t. Right? And there's some growing function, a log t, t to the 2/3, or a constant. Okay, that's the special case, doesn't do much. People usually give this a different name. I don't know why, but people like to use the letter D for some reason. So people call this D, and they put a little plus on it to remind you that it's growing. Okay. So this is a differential equation. I'm going to draw it in a minute, but I just want to say something more about the structure of the solution. This differential equation, right, if I was in, say, K space, I put a K here, our prefactors can depend on K. Right? If I'm in position space, then the Fourier transform of this would be the Fourier transform of B times D. So these equations, first of all, have a very nice property that the space and time has factorized. Is what happens when the CS squared you set to 0, because it was only the CS squared that had a K squared in our differential equation. So because of this, the spatial structure and the temporal structure factorize. Let me write this in another way. I always like writing things that the constant proportionality is manifestly true. I can write this as delta K, let's say of t, is delta K at some initial time times d plus of t over d plus of t initial. This d is called the growth function. So d plus is log t, proportional to, in radiation, t to the 2/3 in matter, and a constant in dark energy era. But first of all, is this okay? So the time dependence completely factorizes in terms of here's the spatial structure and here's the temporal structure. Or in position space, I can trivially Fourier transform this and say that delta of x comma t is an initial delta of x t initial times the growth factor. So I just made it manifestly true at t equals ti. All right. So all I have to do with that being said is that take whatever that initial thing I drew, which was red, and just at the later time redraw it with the identically same shape, because here's the shape, and then just multiply it by a different number. So it literally just gets scaled up. Okay, so at later time, in the way I've drawn it here, if I just focus on the growing mode, I'll put in my nodes to guide my eye. Delta, which is the perturbation, I should just draw it if it, let's say D is 5 or something, I should just draw it 5 times higher. So something like this. And well, if that one's deeper, maybe let's make it clearer, right? This one doesn't have to be constant amplitude fluctuations. Maybe the red has a dip like this, and so I should draw 5 times that, and so forth. Okay. So that's what this linear analysis predicts. If you're focusing on just the growing mode, it just scales up. That's all. And its spatial structure, the pattern is frozen in. It factorizes. We can let's maybe draw this in a slightly different way. Oh yeah, so remember we have a system here that conserves the mass of this stuff. Okay, I write rho. This is all for rho matter or rho dark. Okay, implicitly. This system conserves mass, right? The amount of dark matter total mass is not changing. We have a continuity equation. And that, you can see, though I didn't necessarily draw it great, should be clear in this picture, right? So this region here that's growing is becoming, there's more mass here. It has to get that mass from somewhere. It can't just appear out of nothing. So the mass that's getting increased here is coming somehow from its neighbors. So the nearby neighbors are losing mass. So if you think of this as a gas of particles, the particles that were here in red, some percentage of them got sucked in by the gravitational pull to the left, and these ones got pulled to the right, and so the mass went up here. Okay, so it should be the case that the integral under the red curve or the blue curve is the same number. In fact, it should be the same as just the integral under the dashed horizontal line. Well, yeah, it should be the same, because the mean of delta is 0. If I draw like a 2D image of this thing, I'm not going to use red and blue the same as over there. Let's say at an initial moment, right? So this is X, this is Y, 2D slice of the universe. Let's say initially, there are some regions, I'll indicate them in blue, where blue means overdense. Okay, and now red will mean underdense. Okay, it's not the same color coding as that. That was in time. This is in just density. So there's, I don't know, another overdense region here, say as an initial condition, and then there should be some red regions here, maybe there and there. Okay, just as an example, little patches that happen to be overdense or underdense. Well, if I take this system over time, right, this denser region is somehow just going to grow. So it's going to come out of the board, let's say more, and that one's going to come less dense. And if you think of this as a gas of particles, it must be that there's just literally a flow of particles towards the denser region. So there's a flow of velocity like this, flowing from here to here, and so on. Is that okay? And we should check that our continuity equation predicts this. Okay, so if you recall from last time, we wrote down the perturbed continuity equation, and we got delta dot is -1/a, the divergence of the velocity field, the peculiar velocity field. Okay, so this equation says, if I focus here, let's say, let's check that this is right. If the velocity is flowing in, okay, so these arrows are the velocity field. It's the velocity of the particles, if you like, or the fluid. So if the velocity is flowing in, that means it has a negative divergence. So that minus cancels that minus. That means delta dot is positive. Okay, so that's all it's saying. Where the velocity flows in, the stuff is getting more dense. The blue is dense. It will get denser over time. And it comes at the expense of the underdense regions. They have to have the velocity flowing out of them, and they're just losing mass because stuff is flowing out. Okay, so the rich get richer and the poor get poorer. We know about that. And this system as well. Okay, so it looks like this over time. So other questions about this? Oh, yeah, yeah.
What is the scale? It's like on the time scale of, say, in the dark energy era, 8 years as the universe is expanding, or do we think of these as very fast on the clock?
Yeah, okay, we're going to come to that. So as written here, like when I have like this, for example. So, for example, if I look at this equation here, if we focus just on the growing mode, if you want to say, all right, when does my density contrast change by a factor of 2? So let's say when I go from, say, 1% inhomogeneity to 2% inhomogeneity, you could ask that question. Well, you see that means that the A has to increase by a factor of 2. And scale factor increasing by a factor of 2 happens roughly on the age of the universe at the time. So loosely, when the universe goes from like a second old to 2 seconds old, the scale factor changes by roughly a factor of 2. It's not quite the same because there's some 2/3 power, but it's on the same order. Is that okay? Yeah, and you go from 1 billion years to 2 billion years, the scale factor changes by a factor of 2 or so, and the density contrast would change roughly by a factor of 2 because of this linear scaling. And the log would be completely different in the radiation era. If you want the density contrast to change by a factor of 2, you may have to wait a very long time because logs are so slow. Yeah. Essentially, yeah, something like this. That's right. Yeah. So we could, if there's time, we can show a little simulation of this. Yeah.
Noticing a bit of a range problem with delta, because it can't go less than -1.
Oh, right.
Ever, we can't have a negative.
Right, right.
So if you have a growing mode, positive or negative, you'll get trouble.
Yeah, that's a good question. So anyone have any thoughts on that? Right, this indicates, yeah, if we just let the system evolve forever, any negative value would eventually, I mean, the dark energy could curtail that, but let's say it was matter dominated forever and ever. It would keep growing linearly in the scale factor or t to the 2/3 in time, and this would predict it would eventually negative, which is not right. So that means the answer is that there's something missing in our equations that would fix that. Anyone have any idea what we might be missing in our equations that would fix this? And so you're worried about basically what would happen if delta itself was -1 or more negative than -1, so that the total density is then negative.
You don't expect it to get there pretty quickly during that era.
Because
we're already.
Yeah. So what did we do in the last couple of lectures? We did a big approximation along the way. It's the linear version of the equations. That's right. Yeah. So these equations, so maybe my blue, we shouldn't take it. This dip here is a bit too much. It's on the edge of whether we should trust these equations. So what we have been solving on the board are linear equations. So we linearize things. And that justification means you can think of delta as your expansion parameter. So we've taken delta, we've assumed that it's small. Okay? And then we threw away any terms that might be ordered delta squared, delta cubed, all the nonlinear stuff. Okay, all that nonlinear stuff is lurking there to prevent this disaster that you're referring to, that the total density would never actually go negative, thanks to all the nonlinear stuff that we've deleted. And you see that problem's only potentially there when delta is as big as -1, which is really getting towards the edge if we can trust the linear theory. Yeah, we want to talk more about that as we go. But there's one other point I want to say about this picture here, okay? So this picture, all you do is take whatever pattern was written down initially, the density inhomogeneities, and then you just scale it up under the linear theory, just rescale. That thing, however, that picture that's so simple to state like that, does rely upon me plotting this thing versus x co-moving. This is all with respect to co-moving x. Or I could do it in k-space co-moving k. If you plot things with respect to the physical position, everything's stretching. Okay, like our wavelengths stretch, as we discussed at the end of last time. So if red is some initial time and blue is a later time, two things are actually happening. Not only is there this growth that I drew on the board, but if I were to plot it in physical distance, I should actually stretch the x-axis as well in physical distance. So just to make that clear, so that is, again, is another reason why co-moving is so nice. I don't have to do all these funny adjustments. But we should bear in mind that, let's say this is red. Okay, x, now let's plot x physical. And then at later times, that same region there, this might be my x physical. So I should rescale the red by the blue and stretch it. It really becomes, if that peak there is something like this, it also has a big wide wavelength to it. Okay, so that's in position space, it's doing these two things at once. Is that okay? Most of the time when people show simulations of this thing, it's all in co-moving. So you just see that picture over there. So you just remember this in the back of your mind. Is that okay? All right. So let's try to stitch these three eras together to get an idea as to what is the total evolution, or if you like, what's the total growth function d throughout all these eras. So let's plot the delta itself. And then we can I'll put scale factor here. It's kind of easiest, and time just to the right. So let's mark on our eras of interest. So here is, let's say, A equality is 1 over 3,600, or T of 47,000 years. And we have to lay down an initial condition. Okay, these equations are not going to tell us that. Let's just suppose that in the early universe, well, we're sure this is true, that the fluctuations are very, very tiny in the early universe. Okay, and we can be quantitative about the actual value probably next time. It's a little bit subtle because different modes of different wave number can, in a way, their values are different for the wave number, in a way that they're the same. It's a little subtle. I have to explain it next time. But as a figure of merit, let's take 10 to the minus 4. Okay, the early universe had very small fluctuations. So let's say here somewhere, well, we can think about all this on a log scale. It's say 10 to the minus 4. So delta initial, let's say, is that value at some very early time in the universe, just a little bit after the Big Bang, at some initial scale factor. Just for the sake of argument, let's assume, I don't know, that we lay this down when the universe is a second old. Okay, just as an example. There's nothing deep about that, but just to get our thinking. Okay, 1 second old. I think we checked on the board the other day when we did a summary of everything. There's a redshift of like 4 billion. Okay. So A here, A initial, let's call it, is 1 over 4 billion. Okay, so let's say we start here. Then what happens is it evolves. This is the radiation era. It evolves logarithmically, is what we found. Okay, so somehow it evolves on a function that looks kind of like this, some boring log function. And then in the matter era, it does something else. So let's try to, first of all, compute what it gets to here. All right, so I'm just going to take as an example delta at t initial equal to 1 second, I don't know, to be 10 to the minus 4. This implies that delta at t equality, or you could write delta of A equality, doesn't matter how you write it, matter radiation equality is the initial value, so delta Ti, times the log, focusing only on the growing mode, log A. Okay, so that means log of A equality over A, what I'm calling A initial. And if you want this to be true at t equals Ti, you have to put our friend the factor of E there, but that's not a big deal. You get what I'm saying? This is a way how you can express the growth. It's just a log growth. Right? Everyone okay with this equation? By definition, it's true when at the initial time. Okay, so this would then be something like 10 to the minus 4 times the log of, I don't know, let's say 4 by 10 to the 9 over 3600 times E. And this number here is like 15. Okay, so this is about 15 times 10 to the minus 4. I guess I can write 1.5 times 10 to the minus 3. It's just as an example. Okay, this pathetic log growth is something. Okay, the density contrast in this simple example from the very early universe grows by, let's say, 15. Now we get to the fun part where we grow in the matter era, right? The radiation era. Now let's go to the matter era. And that goes all the way out to a matter vacuum equality. I think I called it once upon a time. That was just yesterday, right? It just when the universe was 10 billion years old. And that happens to be when the scale factor about 0.75 we showed at some point. Okay, so this is a T of about 10 gigayears, just yesterday. Okay, so the growth in this era, what's the growth here that we derived 10 minutes ago? What kind of growth? Linear in the scale factor. That's the big deal. So this log has to interpolate to become a linear function somehow. So let's just sketch that. It's going to do, I don't know, something like this. And then some nice linear thing. This is log A. This is A. Some prefactors. Okay, so then the growth from here to here is very simple. You just take the ratio of these scale factors. That's the growth. So delta at T matter vacuum equality is then I just take the previous answer times A at matter vacuum equality over A at matter radiation equality that we just call AEQ. Is that all right? I just go from this value to that. So this is about a factor of 3,000. Okay. So the universe has grown by around about a factor of 3,000 from here to here. If you look at the scale factors, so that we pick up a big enhancement. So this is, well, if I were to be precise, 1.5 times 10 to the minus 3 times 0.75 times 3600. Okay, this is about 4. So this here, you take these estimates seriously, this is about 4. It's a big change. And then beyond that is the dark energy era. And we didn't really get any growth in the dark energy era. So what it really wants to do is asymptote to the constant. So I should, I don't know, put a little bit of smooth, some nice smooth curve to a constant. Okay, so it's going to do something like this. So we're not going to pick up much in that last little era. So we can truncate this at about 4 by these estimates. Does everyone follow this? So it's not bad. So we start off at 10 to the minus 4, and there's a reason I picked this kind of number. A slightly more precise number is just a little less than that, maybe 5 times 10 to the minus 5, maybe half this, something like that. But if you take these estimates, you're getting up to something like 4. Delta of 1 is a very important figure of merit, right? So let's mention delta of 1. So put it here. When delta is getting around about 1, right, our system becoming very nonlinear. So in fact, this part of the curve here, we should, by this discussion we just had, we should not even take this part too seriously, as delta is bigger than 1, right? Nonlinear effects. So really, we should worry about nonlinear corrections that are important. But nevertheless, the linear theory has taught us something. We can trust it here. And it's telling us that delta does indeed want to get to 1 in before we hit the dark energy era. So it's predicting that the density perturbations will grow, get to around about 1. At that point, you have to say, all right, I should actually do a nonlinear analysis, which really means solving it on a computer, the nonlinear equations. But it has predicted that delta should get up to that nonlinear regime. So it's a regime where density contrasts are so big that you can imagine the mass, the excess mass in these inhomogeneous regions may be so big that that region can hold itself together instead of just expanding with the universe. Okay, so let's just draw a picture of that again. Kind of like what I did over there. So let's just draw this one more time. Let's think of delta as being about 1, right? So let's say delta 1 basically means, you have stuff that looks like this. This is delta order 1. Right? That size is comparable to that size, the background value. So if you look at the excess mass that's lurking, say, in this bit of the universe here, that has so much extra mass that it's sort of not so clear anymore that it just wants these points here in physical coordinates. You normally think the particles are just spreading out with the universe in physical coordinates. But this sees so much extra mass that if you like, the additional force provided by this becomes on the same order as the kind of force that's allowing it to just expand with the universe. That's basically what happens when delta is order 1. Okay, the local force that's holding it together is on the same size as the background value that's allowing it to expand essentially with inertia curtailed by gravity. I was going to go through a little calculation of that, but maybe I won't do that right now because we're running out of time. But delta 1 is a kind of figure of merit. For, let's say, for a region to separate from the expansion and then potentially collapse. Let's maybe we can see a quick movie of this stuff. Hopefully it will light up. Need something else? No, I think it should do it. You mean it's too bright here? Yeah, well, we can. Okay, so this little simulation here is kind of an old, rather old one that someone wrote. Um, the initial in this case is not my t of 1 second, which is a redshift of 4 billion. You see, the initial is 28. Okay, so we're starting much later. Redshift of 28 is already deep into the matter era. Now, that first of all is a sensible thing to do because the linear theory is very good at high redshift. If you start off at, say, 10 to the minus 4. You don't want to waste your computational resources solving the full nonlinear equations, which is what this simulation does. It's much easier to solve the linear theory. Linearly, almost analytically, you can solve it all the way up to z of a few, let's say z of 28. And then from that moment onwards, you run the calculation. Remember, in physical space, this thing is stretching. So if you wanted to start at a z of 4 billion, which is t of 1 second, right, and actually run your simulation, it's a numerical nightmare. Because that means that your box in physical coordinates will stretch by a factor of 4 billion. Right? So whenever you do a simulation, right, first of all, you don't track every point in space, right? You have to have a discrete lattice of points. So imagine your lattice stretches by a factor of 4 billion. Imagine what kind of resolution will you have by the end of your simulation where the lattice spacing is 4 billion. It'd be terrible, right? So unless you started off with, a trillion lattice points in each direction, which is a trillion cubed, you're dead, okay? So it's much better to start off with, say, a stretching of only 28. Okay, then maybe you could have a, lattice points of even 1,000 or something, or 10,000 cubed. It's doable. So anyway, so that's where the linear theory is, that we didn't just do it on the board for sake. It has real power. But then at small z, or more recent times, we do need the power of a simulation. Here's a rather quick movie. Okay, so it's something like this. It's pure dark matter. They're just solving the nonlinear equations we wrote on the board. Nothing abstract. Okay, for a while, it does basically the linear evolution that we talked about. And you can see as an initial condition, these are rather small density contrasts to be sure. And it's just growing under gravity. And then finally, as I said, this is co-moving coordinates, right? Physically, this box stretches by 28. They're just not showing that to you in this. This is all co-moving. Okay, and when the deltas are order 1, as I said, there are regions that are separating out, and it looks like regions that are collapsing to galaxies, clusters of galaxies, and so on. Okay, it's dark matter only, so this is just density contrasts that you're actually seeing. It's not meant to be literally be the light from these regions, but you could imagine it to be so. And then another view of this one is just this, which is the same thing, but just allowing for rotation. Okay, and certainly at the nonlinear level, there's a lot of interesting stuff that emerges. So I just on the board sketch a few over densities, but it's a lot richer going on when you have a full-blown 3D simulation. It kind of looks like filamentary structures and so on that emerge. Because really the initial condition is this totally messy state with also in K-space is many, many, many modes that you're adding up. So there's all sorts of structures that can emerge on different scales. That somehow survives. Most of the structure, though, however, you notice, ends up on relatively small scales. Right? There's not a huge mode that's like over the whole thing. The modes are still on smaller scales. That is something we need to can be understood. That's encoded ultimately in the initial conditions. We could cook up initial conditions such that you have giant density contrasts at late times on very large scales. So the universe had these big stuff like this on huge scales, like gigaparsecs. Our observations indicate that that's relatively small. Or maybe you're going to say some other point of view. But it's usually thought that on large scales, the fluctuations are small, and it's on smaller scales. And that's actually a fact that we have to trace back to our initial conditions. So the prefactor here, whether you specify it in K-space or position space, I have to tell you what that is. It'll actually be much cleaner to talk about it in K-space. The statement would be that for very, very tiny K, the longer scales, this delta is very small. And for higher K, smaller scales, this delta is a little bit bigger. Okay, that's connected to the fact that one ends up with bigger structure on smaller scales. It's not some it didn't have to have been like that a priori from the equations we've been looking at, linear or nonlinear. All right, any questions about this? All right, we'll see you next time.